Hi, welcome to week 4 of 12 Maths B. Today we're going to look at a review of trigonometry and we're going to introduce the derivatives of cos and sine. So to start with our learning goal, we're going to revise finding exact values of trig ratios, sketching trig functions, and like I said, we're going to introduce derivatives of trig functions, or trig ratios as well. So with our exact values, this all should be fairly familiar to you. We're after exact values of sine 45 degrees, 30 degrees and 60 degrees. For the 45 degrees we start with our right angle triangle with sides of 1 and 1, and using Pythagoras it gives us a hypotenuse of root 2. So sine of 45 opposite over hypotenuse is 1 over root 2, cos 45 is 1 over root 2, and tan is 1 over 1, which is just 1. Likewise with our 30-60 triangle here, we start with a equilateral triangle with 60 degrees in each corner. Split that down the middle, gives us a 30 degree angle at the top here. Each of those sides of the equilateral was 2, meaning that there's 1 here, and again using trigonometry, Pythagoras, will give us a side of root 3. And we use this to come up with our exact values. So sine of 60 degrees is going to be root 3 over 2. Cos of 60 is going to be 1 over 2. Draw those triangles in your book and you'll need to memorize them. So from those triangles we can come up with a table like this. Sine of 30 is a half, sine of 45 is 1 over root 2, and sine of 60 is root 3 over 2. Need to know these. Again, write those in your books, learn them. Now, depending on which angle, what quadrant our angle is in, they're going to have different positive or negative values. So we use our cast diagram. So in the first quadrant, all the angle trig ratios are positive. In the second quadrant, only the sine angle ratios are positive. In the third, only the tan ratios are positive, and in the fourth, only the cos ratios are positive. Again, that diagram is something you'll need to remember. So if we look at an example here, we want to find the exact value of sine 225 degrees. First start by putting in where that sine 225 degrees is. We start here at 0 degrees, working anti-clockwise around. That's 180, that's 270, so our 225 is going to be in here. And what we're interested in is the angle to or from the horizontal. So from here, from 0 degrees to 180 is 180, obviously, meaning this angle in here is going to be 45 degrees. So there is 180, from the horizontal down is 45 degrees. Now it's sine 225, so if we look at our triangle, our cast diagram, CAST, we can see that only the tan ratio is positive in the third quadrant, which means just playing with this. It means that sine 225 degrees equals negative sine 45 degrees, because it is in that third quadrant, and we know that the exact value of sine 45 degrees is negative 1 over root 2. Now if we're looking at the second example, we want to find the exact value of cos 11 pi over 6. This is the same as we've looked at before. We start with 0, and if we're in radians now, this is also 2 pi. This would be pi over 2, and this would be pi, and 3 pi over 2. So where does 11 pi over 6 fit? Well, it's not quite 2 pi, it's going to be in this quadrant here, and this angle here is going to be pi over 6. So if we apply our cast diagram, it's in the 4th quadrant, so cos values are positive, cos trig ratios are positive. So over here, our cos 11 pi over 6 equals plus or positive cos pi over 6. Using our exact values, that gives us a value of root 3 over 2. In the interest of saving a bit of time, I'll let you have a go at that one there, work it out for yourself, have a go at it, work out what where the angle sits and what the cast diagram says the ratio should be. If you want to pause it now, I'll put the working on the next slide. So there's the solution for that one. So sketching trig functions is what we're moving on to now. This should be fairly familiar to you from grade 11. This is what a basic sine function looks like. Things to notice where the zeros are at. So we've got a 0 at 0, a pi, 2 pi, and so on. Maximum, we've got one at pi over 2, and a minimum at 3 pi over 2. Max value being 1, minimum value being -1. Again, draw that diagram. You'll need to know the properties of those sine functions. Likewise with the cos function, you need to know what the properties are, what it looks like. So max and min at -1, we have a max here when x equals 0, and when x equals minimum at minimum at pi, and we cross the x-axis at pi over 2 and 3 pi over 2. Tan functions aren't that, you don't use it as much as compared to the sine and cos, but it's worth knowing what they are. Just remember, point of inflection, we reach a limit here at pi over 2 and -pi over 2. So sketching trig functions, you should remember from last year that the general form is y equals a sine b x plus c plus d, where a is the amplitude, b is your frequency, your period is given by 2 pi over b, and the period is how long it is before the pattern repeats itself. C is our horizontal displacement, so we have a phase shift, and d is our vertical displacement. So C is going to push it along the x-axis, D is going to push it up the y-axis. So there's a couple of methods we can do when we're sketching trig functions. We can either use the translations and changes in scale from the original sine and cos ratios to draw or sketch the new function that we're interested in, or what I prefer to do is identify the points where the zeros, the maximum and minimum are, the period and the starting point. Plot these points on a Cartesian coordinates and then graph them, joining the dots. So to work through this, as an example, we're going to determine the amplitude, frequency, period, phase shift and vertical displacement of this function, and then go ahead and sketch the function. So if we get that, rewrite that function in the form that we were familiar with, in the general form, being a sine b x plus c plus d, we take that 2x, or take the 2 outside the brackets, meaning that our amplitude is going to be 4. Go to the next page. Our amplitude is going to be 4. Our frequency is 2. Our period is 2 pi over 2, which is pi. So this curve is going to repeat itself every pi radians. Our phase shift here is to the left, pi over 12, and our vertical displacement is -3, so it's going to be moved to the left and downwards based on our values there. Like I said, now I prefer to use identifying key points as my method of sketching functions, so I'm going to look at that now. So the basic property of a sine function is that it has a maximum of 1. Regardless of what's in these brackets, the maximum value that sine x can have is 1. Alright, so look at what our maximum y value is going to be. This 4 stays here. The maximum value of this section here is 1, and we've got the minus 3. So 4 times 1 minus 3 is 1. So the maximum y value is going to be 1. Now, when does those maximums occur on the x-axis? We have a maximum, sine x is a max at pi over 2. And so what's inside these brackets, if we can equate that to x equal pi over 2, we can determine when that x value is going to be at a maximum. So what I've done here, I've equated 2x plus pi over 6 to be pi over 2, and I just solve for x, and it gives me a maximum of amount. So the maximum of this trig function is going to be at pi over 6, and the maximum value is 1. Now since the period is pi, that's going to repeat itself. Likewise with the minima, minimum value of sine x is negative 1. 4 times negative 1 minus 3 gives us a minimum of negative 7. Maximum, that should be a minimum, sorry. Minimum values occur at 3 pi over 2. So I equate what's inside these brackets to 3 pi over 2, and I solve for x. And so I get my minimum value is going to be at 4 pi over 6 and negative 7. The zeros, assign 0 equals 0. And like I said, we use that phase shift. That phase shift is going to push it across that to negative pi over 12. And when sine equals 0, we've got that horizontal displacement of negative 3. So we're going to have a 0 at this point here. Or that's going to be another point on our curve. And because the period is pi, the next point at negative 3 will be at 11 pi over 2. So we plot those points, and then we can just sketch that graph. I've just used a digital Desmos program. So the derivatives are going to be a bit pushed for time here, but I might do an additional one to include some examples. The derivatives of sine and cos. We looked at this in our assignment last year for grade 11, and you would have started with plotting a trig function and then finding the tangents at various points on that sine or cos function and plotting those values, and you would have determined that the derivative of the sine function is cos, or vice versa, depending on what the what the actual assignment was. But the derivative of sine x equals cos x, and the derivative of cos x equals negative sine x. Now these values are just something you need to memorize. We'll be using them a lot this term, so it's important to be familiar with them and be able to be accurate with them. The biggest difference is just this negative sine x value. Okay, and that's provided that x is a real number and it's in radian measure. And with these derivatives, the chain and product and quotient rules still apply. This video is going to end shortly. I'm going to create another video that's going to run through some of these examples of using derivatives of sine and cos.